Hello everyone, I'm Norman Wildberger. We're looking at box arithmetic, and today I want to move towards a really classical result in number theory, going back to Euler, and I want to show you that box arithmetic presents us with an opportunity of thinking about classical number theory results like this in a new and exciting way. In fact, perhaps a more logical way than we currently have. This is also going to be an opportunity for me to review some important things that we've already talked about in box arithmetic and to go a little bit further and introduce some more ideas. And I'm hoping that you're going to see that this box arithmetic has some kind of naturalness to it. There's almost a sense of inevitability about some of the things that are going on. Just everything's just sort of slot together in a very pleasant way. So this is an opportunity of really rethinking a lot of the elements in our mathematical landscape, starting from a very foundational point of view. Okay, so the result we're going to be talking about is the Euler product for the so-called zeta function, the Riemann zeta function. So let's introduce that in the following way. So the zeta function comes about by looking at a series like this. So let's start with n, a natural number. Then zeta of n is the sum of the reciprocals 1 over k to the n, k going from 1 to infinity. This is the classical definition. So 1 plus 1 over 2 to the n plus 1 over 3 to the n plus 1 over 4 to the n plus and so on. So we think of n as being a natural number like 5, and we think of this as defining a real number, okay, by this process of performing this infinite number of arithmetical operations, always adding smaller and smaller objects to the total. Now this is seriously problematic from my point of view, because in my world you're not allowed to do arithmetic with an infinite number of things. That's not how our arithmetical operations are defined. They are typically binary operations. Okay, you can add numbers 2 at a time, but you can't add suddenly an infinite number of things. And moreover, even before you get to the infinite number of things, the numbers that you're adding here are getting so small, but the denominators are getting so huge that these totals that we're getting, so at any given time, the total that we're getting is some huge rational number, which ultimately blows out on us beyond the size of the universe. So long before we get to infinity, we are stymied here in just adding up these finite series. So that's the whole thing is seriously problematic, having to do with the essential nature of the objects that we're studying. But let us carry on with the usual story. Okay, the usual story is that this real number that we've obtained here for a fixed n is equal to this product. Okay, so it's a product over p prime numbers, 1 over 1 minus p to the minus n. This was written down by Leonhard Euler, I guess actually perhaps in his thesis, and published in 1737. And what is this thing here? Well, it's a product of things, and each one of these things is actually the result of a so-called geometric series. So if you take 1 plus 1 over 2 to the n plus 1 over 2 to the 2n plus 1 over 2 to the 3n, that's a geometric series with first term 1 and ratio 1 over 2 to the n. We're multiplying by 1 over 2 to the n all the time. So the formula for such a thing is 1 over 1 minus this common ratio. So 1 over 2 to the n, or 2 to the minus n. Okay? That's the formula for when p is 2. This is the formula when p equals 3, and then when p equals 5, and then when p equals 7, and then when p equals 11, etc. So if we have n, a fixed natural number, this is supposed to be a real number. Again, the result of an infinite number of processes. Again, the result of an infinite arithmetical calculation. And we have one of these for each prime. And as we go further on here, these numbers are getting closer to 1 because the things that we're adding to 1 are getting really small. So these are numbers, real numbers with decimal expansions that start like 1.0000, a whole bunch of zeros, and then some stuff. And the idea is that, well, one can prove a kind of a convergence in the usual fashion, that this product here sort of stabilizes, supposedly, converges to yet another real number. And the claim is that that real number that you're obtaining here with this infinite product is equal to this earlier real number that you obtained with this infinite series. So although I think this is entirely problematic, it is a very standard sort of starting point for a huge amount of analytic number theory. But my aim is to try to see if we can think about what's really going on here. There's something really interesting going on here, but I want to be able to access that in a more logical, correct way. And I think that box arithmetic provides some kind of framework for creating such an alternative, more logical framework. And that's what we're going to be talking about today in this video, which is going to be a little bit long because there's quite a lot of things to talk about. All right, so box arithmetic is an attempt to set up the foundations of arithmetic from a multi-set point of view. So not using set theory, but using multi-set theory, which is a more flexible environment and allows us to do certain things that we're not able to do in the set theory world. Now, I'm going to give you just a simplified version of this. In particular, I'm not going to talk about the exciting developments that result from introducing anti-boxes, okay? So we're just going to stick with the simple version here. So in the world of boxes, we start with 0, which is just an empty box. So everything is kind of a box in this world, but the boxes can contain other boxes, and so they can be nested, okay? So the simplest box is just a single empty box, and that has the name 0. If we put a bunch of these zeros inside a box, then we get a natural number. So that's the natural number 1, that's the natural number 2, etc. And then if we put this one here inside a box, so this thing here represents a box which contains a box which contains a box, if we were just writing it in terms of boxes. So that's a new kind of object. We might call that alpha. This is the box containing 2, it's alpha squared, and here we get the Pauli numbers, okay? So 0, then here are the natural numbers, here are the Pauli numbers, or polynomials in one variable. And then if we nest further, if we take one of these and put it in a box, we get what's called a multi-number, okay? And then there's a sequence of multi-numbers like this. And the whole thing keeps on going because we can just keep nesting these things. And actually, we don't have a lot of experience with the vastness that goes on below here, right? But there is an arithmetic that's, that's in theory accessible to us that we can investigate. But actually, for standard algebra, actually just these levels are pretty interesting. But today we're going to see that the multi-level is also quite interesting and has direct applications to number theory. Now, associated to this natural hierarchy, there's also sort of counting objects. So we introduce Z. So Z of any box A is, by definition, 0. So it doesn't matter what you've got. If you apply Z to it, you get 0. Then n of A is again an arbitrary box in this world. N of A is the box that consists of all Z of A, where A is an element in A. So if we're talking about a box like this, right, the elements are, this is an element, this is an element, and this is an element. So all the boxes that are directly inside the box that you're considering, those are the elements of the box. So basically what we're doing here when we're applying n of A is we're replacing all of the objects with 0, and that results in a natural number, okay, and that natural number is the size. We're counting how big the original box was in some sense. So that's the n of a counting object. So for example, this thing here, we replace each one of these guys with just a 0, and then this thing here we recognize, oh, that's the natural number 3. Okay, so then there's a natural inductive story here. In fact, there's a natural inductive story pretty well for everything that we do here. Okay, everything just keeps on going down. So P of A is then the box consisting of the n of A's as we run through the elements of A. So here is some box. If we apply P to it, what we have to do is we have to apply n to each one of its elements. So it has 1, 2, 3, 4, 5 elements. N of this thing is 0 because this has 0 things in it. N of this thing is 2 because it has 2 things in it. N of this and this are also 0. And this one here also has 2 elements in it. So n of this is 2. So applying P to this box here gives this box here. This is a box containing natural numbers, so it's sort of at the Pauli level, okay? And in fact, it's 3 plus 2 alpha squared. a single 2 is like an alpha squared, and there's 2 of them, so we get 3 plus 2 alpha squared. And so typically when we're counting like this, what we're getting as a result of the count is an element in one of these levels. And as we go further down, well, the object that we're getting as a result of the count is more and more sophisticated. So for example, the next level would be, say, M of A, where we, for any box A, we consider the box of P of A's, where A is in A. So this is an inductive or a recursive way of introducing these counting functions, if we like. All right, so to have a nice arithmetic, we need some operations. The first operation is addition. So given any 2 boxes, addition is just what you get when you dump the contents of both of those boxes into a new box. That's a very elementary kind of thing that you can do in the multiset world that you can't do in the set world. Okay? So this is really the critical operation upon which everything is based. So this box plus this box, just dump them all in. We get 1, 1, 1, there's a 2, and there's a 3. So that's the result of adding these boxes. When we multiply boxes, what we do is we use the previously defined operation of addition. So what we're going to do is we're going to take the sum of all possible pairs of an element here and an element here. So we take this plus this, which is 2, this plus this, which is 4, this plus this, which is 2, this plus this, which is 4, this plus this, which is 3, this plus this, which is 5. So that's how we multiply 2 boxes. And again, all these operations are not restricted to any one level. So this is not just an operation on natural numbers. No, it's an operation on any of the boxes, no matter how complicated or how far down they are in the hierarchy. Okay, then the next operation, which we call the caret operation, it's sort of like an exponential in some ways, but it's not really an exponential. It's something a little bit different. Here's a box to find the caret of them. Again, we perform all possible combinations where we take one here and one here, but now we multiply those 2. Okay? We use the previously defined operation. So 1 times 1 is 1, 1 times 3 is 3, 1 times 1 is 1, 1 times 3 is 3, 2 times 1 is 2, and 2 times 3 is 6. So this M set, or this box, caret this M set or this box is this M set or box. And clearly, we can just carry on. We have more and more complicated operations starting from these simple ones: addition, multiplication, caret. So these operations are all commutative and associative. And just to practice a few more carets, which are going to be sort of the main focus for today's talk. So here's another box. We have to multiply them. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. Okay, easy. How about this one? 1, 2, caret 1, 2. Well, 1 times 1 is 1, 1 times 2 is 2, 2 times 1 is 2, and 2 times 2 is 4. And let's introduce this sort of simplified, more concise way of representing the multiplicity here, right? This 2 is occurring with multiplicity 2. So let this little index on the left, lower left, represent the multiplicity with which this object is occurring. Just a way of writing things out a little bit more efficiently. So for example, if we take the M set 1, 2, and we perform caret to the 3. In other words, we take this box, caret itself, okay? Then it's like taking this thing here and careting it once more with a box 1, 2. Well, you can check that we're going to get a box with just 1s, 2s, 4s, and 8s. There's going to be 1, 1. There's going to be 3 2s. There's going to be 3 4s. And there's going to be a single 8. Okay, so now that we have operations, I can write down a few counting laws. So some laws that our counting functions satisfy. And I've given some examples. I'm not going to go through them all. You can check them. Hopefully I haven't made any errors, but I don't guarantee it. So the first one is that n of a plus b is n of a plus n of b. And you know, if I say not otherwise, A and B are just arbitrary boxes. Doesn't matter what they have in them. Okay, so if we take the sum of two boxes, we'll say like these ones here, okay, there's the sum, just what you get when you dump them all in, okay, and you count the number in the sum, well that's 5, and the number here is 2, and the number here is 3, and 2 plus 3 is 5. So this is kind of obvious. Remember, multiplicities count for something, right? So, you know, there's two 2's here. They each count as being an element. So there's one element, another element, and another element. There's 3 elements in that box. If we look at P of A times B, well, that's P of A times P of B. So here's a box, and here's another box, and multiplying them, we have to take the sum of all the possible combinations. So 2 plus 1 is 3. 2 plus this thing, well, 2 is really the box containing 0, 0. So if we add this one and this one, we get the box containing 0, 0, alpha. Well, you can think of this one as being really the box containing 0. So if we take this one and add this one, we get the box containing 0 and 3. And if we add this one and this one, we get the box containing 3 and alpha. And then P of these things, well, we have to replace each one of these by their sizes. So this has size 2. This is a box of size 2 in the sense that n of it is 2. This is a box that just has one thing in it, so its size is 1. So this is replaced with 2 and 1. Here, this one's replaced with 1, 1. And when we perform the product of these two boxes, well, we have to take all possible sums. 2 plus 1 is 3, 2 plus 1 is 3, 1 plus 1 is 2, 1 plus 1 is 2. And we see that these numbers here count the numbers, the sizes of these things. That's got 3 elements, that's got 3 elements, that's got 2 elements, that's got 2 elements. Okay, and then there's a corresponding one for the caret. That m of a caret b is m of a caret m of b. And here is an a, here is a b, here's my attempt at writing down the caret. Okay, and over here are the m's of these things. So here's m of this, here's m of this, and here's m of this. And I'll let you stare at that and convince yourself, I hope, that I've done it correctly and that this law is being reflected here. So in this series so far, we haven't looked at the caret operation too much, but that's going to be, as I've mentioned before, very important for us to try to understand this zeta function Euler product identity. So let's have a little bit more practice with that. So here, for example, is another application. So you can sort of see the binomial theorem again in caret form, that if we take 1a and we take the caret to the 4th power, so this box, caret itself, caret itself, caret itself, okay? So we're taking all possible products of entries here, okay? So we'll end up getting a box with elements 1, a squared, a cubed, and a to the 4th, okay? And the multiplicities of those things are 1, 4, 6, 4, 1. And you can see this is just a form of the binomial theorem in this box arithmetic world. Let's go a little bit further and consider maybe a trinomial. So let's consider a box with 3 things, say 1, 2, and 2 squared, and caret with itself. So what are we going to get? Well, we're going to get 1 times 1, 1 times 2, 1 times 2 squared. We get 2 times 1, 2 times 2, 2 times 2 squared, and 2 squared times 1, 2 squared times 2, and 2 squared times 2 squared. And then when we think about that, we're getting the elements 1, like 1 times 1 is 1. We're getting 2, 1 times 2, and 2 times 1. We're getting actually 2 of them. And how many 2 squareds are we getting? Well, we're getting this one here, we're getting this one here, and we're getting this one here. There's 3 of them. And how many t cubes are we getting? Well, we're getting this 2 times this 2 squared, and this 2 squared times this 2. So there's 2 of them. And there's only 1 2 to the 4th. So we're getting 1, 2, 3, 2, 1 as the coefficients. If we jack that up a little bit and take 1, 2, 2 squared, 2 cubed, so an M set with 4 things, and we again form a squared caret operation of that, well, we're getting, again, the sequence of powers, and the coefficients go up linearly, 1, 2, 3, 4 to a max, and then back down 3, 2, 1. And more generally, if we have, say, 1a, a squared, a cubed, and we take the caret square of that, we're going to get 1a, a squared, all the way up to a to the 6, with coefficients 1, 2, 3, 4, 3, 2, 1, just as in this case here. So there's sort of a potential for just thinking about algebraic identities, perhaps familiar ones, but maybe just using a different language. Maybe this shows us something new for us, maybe it gives us a little bit of additional insight into otherwise familiar things. But maybe it also allows us to discover new things. Well, oftentimes patterns are most easily seen when we allow them to keep on going, where we don't insist that we go up to some point and then stop, but just let some natural sequence just keep on going. That, of course, involves logical issues because we have to interpret what we mean by any arithmetical statements involving such ongoing things. That's an important issue for the algebraic calculus course. For example, in the algebraic calculus 2 course, we're looking at essentially power series, but we want to interpret them in ultimately a kind of a finite, explicit way, where we are not assuming that we're able to do an infinite number of things, even though something is going on, beyond our view. So we almost have to adopt an ancient Greek point of view towards these things. That's what we're going to do here. So there's some logical issues now that need to be clarified before we have a correct theory along the lines I'm going to suggest now. And I'm just outlining some further directions later on we can think about, okay? But there's some patterns here that I want us to become aware of. And it's an interesting story. So let's have a look at sort of some ongoing versions of what we just wrote down. So let's consider a box whose entries are 1, a squared, a cubed, etc. So a here is potentially just another box, okay? And we're taking the caret squared of this thing here. So taking this thing and careting it with itself, forming all possible products. Well, we're going to get a 1. We're going to get, because 1 times 1 is 1. We're going to get an a, like 1 times the second a, and also a times the second 1. Okay, we're going to get an a squared, and that's going to appear in 3 different ways. We're going to get an a cubed, that's going to appear in 4 different ways. So what we're getting is an ongoing sequence where we also have all the increasing powers of a, but the coefficients are 1, 2, 3, 4, 5, just the natural numbers in their natural sequence. Now if we do something just a little bit more sophisticated and look at the third caret of the same thing, in other words, multiply this thing by this thing again in the caret sense, caret this with this, then we're getting a similar kind of sequence, but now the coefficients are 1, 3, 6, 10, 15, etc. We recognize the triangular numbers. And if we do caret to the 4th power, you can check that we're going to get a similar series with coefficients which are the pyramidal numbers, 1, 4, 10, 20, 35, etc. So what we're doing here is we're touching base with one of our favorite objects, the Harriot-Pascal array. It features prominently in the algebraic calculus, of course in many other areas of mathematics. So we can think about it like this. So it's like a Pascal triangle. And the columns here, sort of the Harriot columns, they're ongoing, okay? And any one of these columns, like triangular numbers, pyramidal numbers, etc., and higher versions of them, they're going to be naturally then appearing as coefficients of these sort of like something like a binomial series, but in the caret world, involving these sort of basic geometrical boxes. All right, so I've given enough structure and examples that I can now show you the main identity of this lecture, which I'm going to call the fundamental identity of arithmetic. So I think this is a really important thing that's right here, okay? And it's, in my view, some kind of box arithmetic equivalent or restatement of the fundamental theorem of arithmetic. And we'll see that it's not very far away from the Euler product for the zeta function. But let's just have a look at it by itself. So we're taking a caret of a bunch of ongoing boxes. They're all of the kind that we've just been talking about, where you have 1 and then 2 and then powers of 2, 2 squared, 2 cubed, etc. going on. Okay? And then the next one is the same kind of thing, but with the prime 3 and its powers. And then the next one is the prime 5 and its powers, and the next one is the prime 7 and its powers. And we keep on going over primes p. And we want to take the caret of all of these. So what does that mean? Well, it means that we're forming a box, okay, whose elements are obtained by taking one element in here, multiplying it by one element here, multiplying it by one element in here, multiplying it by one element in here, etc. Well, obviously we need to say a little bit more precisely what we mean by that, because we don't want to be multiplying an infinite number of things together. So we'll agree that the kinds of products that we're considering in this ongoing caret product are ones where only a finite number of the elements that we're picking are not equal to 1. So most of the time, the element that we choose from one of these boxes is 1. Or to put it another way, once we get to a certain point, then from that point on, we're only going to be choosing the 1 in all subsequent boxes. Okay? So we might, for example, choose 2 squared times 3 times 5 cubed, and then after that, just 1, 1, 1, 1, 1. And then, so the number that we would have gotten would be a 2 squared times, let's say, maybe 3 times 5 cubed, whatever that is. Okay, and the statement is that in the world of box arithmetic, suitably defined, suitably interpreted, that the result of this ongoing caret product is this box. The box just consisting of the natural numbers starting with 1. 1, 2, 3, 4, etc. So this is a statement of box arithmetic. And it's not too hard to see that this is really somehow equivalent to the fundamental theorem of arithmetic. What we're saying is that any number, any natural number, like 12, okay, 12, is going to appear exactly once in this product. In fact, we know what it's going to be. It's going to be obtained by taking this 2 squared and that 3, and all the others are going to be 1. So we're just taking the appropriate prime power factors of whatever number we're talking about. Okay? So this is just a restatement in the world of box arithmetic of the fundamental theorem of arithmetic. But it's interesting to think about it that way. Now let me introduce the summation operator, or the sum operator, capital S, which is like a counting function, but it's a little bit different. Okay, we're going to define S of A is a box, to be the sum of little a in A of A. So the elements of a box are boxes, and we can always add boxes. So what we're going to do is we're just going to add up all the boxes which are inside A, which are elements of A. We're going to call this the sum of capital A. So for example, what's S of 3? Well, 3 is officially this box here. It's the box containing a 0, a 0, and a 0. So S of that is what you get when you add up all these elements. So 0 plus 0 plus 0. And that total is 0. So S of 3 is 0. And in fact, S of any natural number is good. Here's S of a polynomial or poly number. 2 plus 3 alpha plus alpha to the 4th. What does this thing actually look like? Well, it's a box. It's got 2 zeros. That's the 2. It's got 3 1s. So that's the 3 alpha. And it's got a 4, representing the alpha to the 4th. So S of that is what you get when you add up all of these elements. 0 plus 0 plus 1 plus 1 plus 1 plus 4, which is 7. So S of this polynumber is 7. Here's something a little bit more sophisticated. So we have a box with 3 boxes inside. This is the box containing 2. This is the box containing both 3 and alpha. It's supposed to be separate. And this is the box containing alpha 1, which is a multi-number. Okay, so S of this is, well, we have to take this box, and this box, and this box, and we have to add them. Well, adding boxes, we just dump them out. So we get the box containing 2, containing 3, containing alpha, and containing alpha 1. So that's just taking the sum of a box. And now there are some summation laws. I'm going to show you 3 of them. It's this third one here that's particularly interesting for us, all right? But let's have a look at the simpler ones first. S of A plus B equals S of A plus S of B. There's a box, there's another box, there's the sum of the boxes. S of this is 1 plus alpha. S of this is 2 plus alpha cubed. S of this thing is 1 plus 2 plus alpha cubed, which is the same as 3 plus alpha cubed. And that's the same as what you get when you add those things. S of A times B is S of A times N of B, the number of elements in B, if you like, plus N of A times S of B. So here's A, say 1 alpha, and we're multiplying it by 2 alpha cubed. So to multiply, we have to take all possible sums. 1 plus 2 is 3, 1 plus this is this, alpha plus 2 is that, and this plus this is that. Okay, that's the product of these two things. So what is S of this? S of this is 1 plus alpha. S of this is 2 plus alpha cubed. What's N of this? Well, it has 2 elements. What's N of this? It's 2 elements. So the right-hand side is S of A plus N of B, that's 2, plus N of A, which is 2, times S of B, which is this. And the claim is that that's equal to the sum of this thing, which is 3 plus this, plus this, plus this, which totals, gives us 6, plus, I guess, 2 alpha, plus 2 alpha cubed. And this equals this. And now, S of A caret B. Claim that S of A caret B is S of A times S of B. So if we use the same guys here, so 1 alpha caret 2 alpha cubed. So to caret something, we have to take products. So 1 times 2 is 2. 1 times alpha cubed is alpha cubed. Alpha times 2 is 2 alpha, and alpha times alpha cubed is alpha to the 4th. S of this is 1 plus alpha. S of this is 2 plus alpha cubed. S of this is 2 plus 2 alpha plus alpha cubed plus alpha to the 4th. And if we multiply these two, we get 2 plus 2 alpha plus alpha cubed plus alpha to the 4th. Naturally, you're thinking, okay, but what about if we keep on going further down in this hierarchy of boxes? What are the corresponding summation laws? What are the corresponding counting laws? This is vast realm of arithmetic, unexplored arithmetic, which you can be the first to explore, to discover. So now let's go back to what we call the fundamental identity of arithmetic and see if this summation law that we've just looked at applies to that and gives us any kind of information. Now this is a delicate operation because we haven't really properly nailed down what we mean by the arithmetic of these unbounded or ongoing boxes. Okay, so there's something to be done there. Hopefully we can frame all of that in a very finite, explicit way so that we're still able to actually make logically correct statements about such things. But if we just say, look at things informally now, so here is something similar to what we wrote down. Remember we had this box of powers of 2, and then box of powers of 3, and box of powers of 5, and then of 7, and we were careting them all together, okay? But now if we apply sort of the S function to everything, well, S of this first box, well, what we have to do is we have to sum all the elements. So that's 1 plus 2 squared plus 2 cubed, etc. There's a sum of the box of powers of 3. There's a sum of the powers of the box with powers of 5, etc. And this law is telling us that we should multiply these things together. We should multiply the sums. And that should be the sum of the caret. Well, the caret is on the right-hand side. The caret was this box of all natural numbers. And S of that is going to be the sum, 1 plus 2 plus 3 plus 4, etc. So very naively, informally, without a good, precise understanding of what this actually means, we're getting, so I should put everything in quotes. Yes, definitely, guys. This is just some kind of idea currently. We have some kind of equality between this summation times this summation times this summation times this summation, etc., equaling this summation. And I claim that this is pretty close to the Euler product story, but we just need to twist things, and that's a new kind of thing, that we have to introduce some sort of multiplicative functional here to convert this thing here into something which converges in the usual analytic sense of things. So that's what we're going to do in our next video. Introduce a twist that will allow us to see the Euler product as a natural manifestation of this law applied to the fundamental identity of arithmetic. I'm Norman Wahlberger. Thanks for listening.